So please, if any team wants any equipment, we can get those equipment. So to build some demos, at least we have 2 screens here. We don't use at the moment. It will be very nice. We can have those demos running here full time. So please, if any team wants any equipment. Yes. So we will go back to slides. Yes. So this is an implementation in Keras. In Keras, it's very simple. There are some implementation in PyTorch, in fact, but I'm very new in PyTorch. Just to try to start learning something in PyTorch. I don't know, but PyTorch is very good in other things, in fact. So but Keras here is very handy and okay. So first we need to build the model. You need to configure your model. You need to train your model. You need to evaluate your model. This is very important. I mean, this is our pipeline which we need to follow. So what does it mean, convolution? So for example, we can start by edge detection, for example. If we have an image, right, we will have some filters or some kernels. Those we will use convolution. So edge detection, for example, is used for image segmentation. We can use it for segmentation to extract some features from the image. It creates boundaries of object to detect the object location. I have some object here, but I want to detect where is the object. So in fact, we can use some vertical edge detection or horizontal edge detection. Each one has its own kernel. People from image processing, they just invented those kernels. So he decided those values. And if you change those values, you will get different thing. Because they have been working maybe visually. I need to detect those vertical edges or horizontal edges. How can we do this? Using those kernels. So this is an example. So we have 6 times 6 input image with 3 times 3 element wise product. We have this kernel. It's 3 times 3, and as you can see here, we have 9 values. So we select this column once, this one zeros, this one -1, right? So this is an image, and if you plot this image, in fact, 0 values, it will be black, maybe 10 will be white. So in fact, this is an image. And we have here an edge. This edge, it's a vertical edge, right? We need to detect this vertical edge. We need to detect it. So in fact, we should get something like this one. It will be white in that edge and black otherwise. So we need to detect this one. How can we get this one from this one? We can get this one from this one using this kernel, right? So they need to invent this kernel. So it will be white also when it's 1. It will be, it will be like this one. Just apply this convolution, for example. So we'll apply this one here to that part. Correct? So when we apply it here, what will happen? This one, it's 1, 2, 3, 4, 5, 6. 6 times 6, this one will be 4. So we will apply it here first. So just multiply. So it will be 30. 30 minus 30. 30 minus 30. It will be 0. So this one will be 0, right? Because this one, it's not edge, in fact. This one, it's not edge. The edge, it's in the middle here. This is the edge. I mean, when you go from 10 to 0, from white to black, we have this edge here. So we need, in fact, we are interested to detect this one. So we will move 1 step, and we will do it 1 more time, right? So in this case, it will be 30, right? It will be 30. 30, it's white, right? 30, it's white, and 0 is black. We will move 1 more step, and we will make this calculation 1 more time. So it will be 30 plus 0, 0. It will be 30 again. 30 also, it will be white. Now we are here. I will move one step here. So the last one, it will be zeros, which is black. So now we can detect the edge in those 2 pixels, right? Using this horizontal, this vertical kernel, vertical edge detection. So this is how it works. So people, in fact, when you open a book in image processing, you can see maybe 5, 6, maybe 10 kernels, which is a use for different applications. So I've been working in a project before. It was building an expert system for psychological symptoms, and I mean, we're asking kids to plot picture, for example, And from these pictures, you can define if the child has a problem or not, if he has been abused at home, for example, or not. You can predict this from a drawing. So you ask the child to plot something, and people from psychology, they check size of face, nose, hands. So if you ask him to plot a person, for example, if he plot a person with big hands, this one has an indication. Maybe he has been punished at home because he focused on this one, right? So from those images, you can detect many things, in fact. So they train people for doing this, but the idea I was in South Korea and I have been working in that project. In fact, we need to build an expert system to help the teachers and families, parents, for example, to run this test at home, for example, or in school. And when they discover that a child has a number which is different than the rest of kids, for example, they can send those to a doctor to check him. Not all people, because it's impossible to send all kids for checking, right? So the idea here is to use an expert system which will replicate what doctors do, in fact, and you can early detect if there is something, there is a symptom or an indication of something. So they can, just for selective kids, they can check them more. So we ask kids to plot things, right? And we need to check what is the volume of the head, right? So we need to detect this edge, right? And calculate volume and find location. So lots of image processing stuff. So I've been working with image. We have been working a lot with those kernels, for example, to detect edges, different types of edges and different types of information. So at the end of each image, we will get some numbers representing those features. And those numbers will be used for training a sample model. At that time, it was feed-forward neural network. So instead of working with a big image, maybe which is 500 times 500 pixels, you can just get some features from the image. Because when you detect vertical edges, I can calculate it. In fact, we can find the size of those vertical edges in the image, because it will be black pixel or white pixel. Because this one, in fact, I can just flip it, right? We can convert white into black and black into white, and we can calculate number of pixels which the edges, for example. So this is one kernel. Those numbers, people from computer vision and the people from image processing, they give us those numbers, and people have been using those numbers for many years, hundreds of years or tens of years or whatever. They have been using this one for edge detection, vertical and horizontal edge detection. But in case of, so we will apply it first for that part. We will get this number, we will apply it again, we will get this one more time, and so on. It takes too much time. Yes, so do you see? So we can get those values, right? Of course, the size, the input image, this place, in fact, in the middle of the image, we covered it more than the rest of the images. So this is the overlap, in fact. So this one here in the middle, it has more overlap, and we covered those areas much less, in fact. The size here, it's 6 times 6. The feature map, it's 4 times 4. We lose those perimeter, right? Because we didn't use 0. We need to add some, how do we call it?
Zero
padding. So if we need to get the feature map the same size as the original image or input volume, we need to use 0 padding, right? We didn't use, so the feature map is too much smaller than this one, right? So in the middle here we have overlap, right? So when you use stride equal 1, we will get some overlap. Maybe if the middle of the image is more important, right? So we can just, using this stride, it will affect this one. Some areas we are covering more than the rest. So we can propose also, you can propose your own filter, for example. This is vertical, this is horizontal, this is horizontally change, right? This is vertical change. So just imagine those numbers, some people carefully, they decided those numbers. maybe trial and error, they came up with those numbers. In deep learning, in fact, we initialize the kernel, because this kernel, for example, if we use 3 times through 3, we have 9 weights. We will initialize those weights with random values, correct? And after that, we will train the model with the data to try to extract something useful for the problem. And for example, here we have 4, but when you select 64 feature maps, it's a huge, big number. So we need to learn, or we need to extract 64 different feature maps. And we will just train those weight values from, from the data by learning our data, fitting our model. So, in deep learning, it will be much stronger, more effective. In fact, we can get something very, very, very important. So I wish also if some of you is training his model, he can try to predict those values. Can you try to print those values, weights? Because we can check if we are using 3 times 3 kernel, for example, we need to see those numbers. How much are those numbers? Is it something which we can realize, for example? Because when you get those feature maps, when you get those kernel values, weights of the kernel, we can just use it. We can test it with some images. When we can see what is there any different, what is the value? What does this one mean, for example? So our capabilities, in fact, if you will do feature extraction manually, our capabilities is different. It's limited. And also, we will try to extract something from our point of view. It might help us and it might not help us. But for the machine, in fact, it will do this process automatically, and it will try to invent new kernel, which will help the problem to be solved correctly because we have a cost function. We have its optimization problem, in fact. We try to find a combination of those weights to increase the performance or accuracy. So it will automatically try to adjust and try to get some weights which will make sense for the problem which we are solving. Yes, padding. What is padding? It's convolving an input of 6 times 6 dimension, which we see in the last slide, with 3 times 3 filter. It resulted in 4 times 4 output, right? So we are shrinking because we didn't use zero padding. So we can generalize it, and it says that if the input is x, is n times n, in fact, and the filter size is f times f, then the output size will be n minus f plus 1. So it will be 6 minus 3 plus 1. So it will be 4 times 4. So if you need to know the size of the feature map, you can calculate it using this formula. Because if the input image is n times n, and the filter size is f times f, so the kernel size will be n minus f plus 1 times n minus f plus 1. For the example in the last slide, the original image was 6 times 6, and the filter size was 3 times 3. So the feature map will be 6 minus 3 plus 1. 6 minus 3 plus 1, it's 4 times 4, right? So there are primarily 2 disadvantages here. Every time we apply convolutional operations, the size of the image shrinks. Each time we apply it, the size will shrink. Pixels present in the corner of the image are used only a few number of times during convolution as compared to the central pixels, leading to information loss. All pixels are in the middle. We will scan it several times, but we will scan pixels in the corners and at edges only a few times, which will lead into some information loss. How can we avoid this? By adding padding. And the padding, it will be according to the filter size. So if you are using 3 times 3, so we will add 2, 2. 1 from here, 1 from here, 1 from here, 1 from here. If the filter size is 5 times 5, so we'll add 2, 2, 2, 2. Right? Yes. Padding, again, to overcome these issues, we can pad the image with an additional border. We can add additional border. We add 1 pixel all around the edges, right? Okay, so now after adding padding, in fact, what will be the size after adding padding? So this means that the input will be an 8. If the input is 8 times 8, okay, this means that the input will be an 8 times 8 matrix instead of 6 times x. So if we need to add padding, right? So instead of working with 6 times 6, it will be 8 times 8. So we will give more importance to the pixels at the edges, because we will scan it more now. Because if it is close to the edge, and if we didn't use zero padding, we will just scan those areas maybe a few times, only a few times. We can see it from the last image. And the pixels at the center, we scanned it several times. So we will extract more information from the central pixels compared to the pixels at the edges and at the corners. How can we avoid this? By adding zero padding. So applying a convolution of 3 times 3 on it will result in 6 times 6. So if we will add padding here, what will be the size? It will be 8 minus 3 plus 1. 8 minus 3 is 5, plus 1 is 6. So it will be the same size, right? There are two common choices for padding. We have this valid and the same. In Keras, we have valid and the same. Valid, it means no padding, right? Padding equals 0. If we are using a valid padding, the output will be n minus f plus 1. It will be just the one which will be shrinked. So just remember, I mean, when it's valid, it means no padding. When it's the same, we apply padding so that the output size is the same as the input size. The input size will be the same as the input size, which means it's just, how can we get this? It's n plus, I mean, the output size will be n plus 2b minus f plus 1 if you have padding. Because in fact, when we add padding, when padding equal, for example, here, for example, if f is 3 times 3, in this case, b will be 1. So it will be, for example, it was 6. So it will be 6 plus 2 minus 3. 6 plus 2, it's 8, minus 3, it's 5, plus 1, it's 6. So it will be the same, right? So the formula, if you want to calculate, if you will use padding, if it's same, so the output size will be n plus 2b minus f plus 1 times the same, because it's squared. In this way, we don't lose a lot of information and the image does not shrink either. So the image will be the same size, and we don't lose so much information from edges, right? But it's still also, we scan central pixels more than pixels at the corners and at the edges, right? But now we are not losing too much information. We lose something, in fact, but we're not losing a lot. Stride and the stride or stride convolution. So suppose we choose a stride of 2. If we choose a stride equal 2, so while convoluting through the image, we will take 2 steps, both in the horizontal and vertical directions separately. We will go, and after that we'll go down. So we will go horizontal, and after that we'll go vertical. Stride helps to reduce the size of the image, right? A stride of 2 or more reduces overlaps, correlations between activations. So we reduce number of calculations. Because when we use a stride, right, we can we reduce the size of the image. Yeah.
Yes.
We reduce the size of the feature map. Yeah. So a stride of 2 or more reduces overlaps and the correlations between activations. We will reduce number of calculations, and this is why we have less computational time when we increase the strides.
Yeah.
But as you said today, this morning, when you increase the stride, correlations and overlaps will decrease. So it's like each part of the image will be independent. It's like in RANN. I mean, Jubairi today, he was talking about independence in the sequence of words. There is kind of independence, correct?
Yes.
So I should explain that it's you. But if we are dealing with each word as independent, we will not be able to predict what will be the next word. So the context, this is the context. So when you increase the stride, we will decrease the correlation and overlap. So we will deal with each part as each receptive field as an independent part of the image. I'm looking here and I'm looking here. There is no connection, right? There is no connection between each receptive field, right? Mm-hmm. So also using a stride, I mean, the output size will be like this one. So the output size, in fact, it's a function of the stride. So the stride will impact, it can do some downsampling similar to pooling, correct? It can downsample. So the size would be n plus 2p minus f divided by s plus 1. So in fact, it's that part divided by s plus 1. So stride of size 2, it's just an example. We are doing this convolution. We do this convolution and we try to check its impact. I don't know if I made some. Okay, so we will apply it here now. We will apply this one in that place, correct? Just multiply and take summation. Multiply, take summation, it will be 91. So the output will be here. Do you see? We will put the output here. Okay, this is okay. And what will be stride? Stride of size 2. So we will move by 2 steps. So now we will move to that place. Correct? So the size, look, this is the first convolution. Second, okay, I don't know. It will be like this one. Yes. We will move 2.
Yes.
Okay. So the size will be, we will have 3 pixels. So we are doing down sampling, in fact. We are doing some down sampling. So, okay. Okay, so we step back again. So we will do it for the second time. It will be 100, right? The third time. So now we can get 83. This one, we will get 96. Yes. So Hossein, I mean, stride also, it will impact many things. It will impact number of activations and the size of the feature map, because we will do some down sampling here.
Yes.
So we need to differentiate between stride and pooling.
Yeah.
Because both of them can.
Yeah.
So you cannot test 2 together. You need to fix all hyperparameters and check one by one. If you really need to get some. So stride also, it's like max pooling or average pooling. We will have the same. The feature map will be much less. It will be shrinked, right? And when this one will be shrinked with down sampling, and when we down sampling, we will reduce number of activation in the next layer, for example. So number of calculations will be less. So in fact here we have 9 calculations. When we select S equal to, we will have 9 calculations, and we reduce the image size. Right? Number of calculations is less. Number of activation is less.
Yes.
Correlations and overlap is much less. So now each part is all. I mean, do you see? You can see it here. Only this column. This is the overlap. Do you see it here?
Yes.
This is the amount of overlap. So we reduce the overlap and correlation between each receptive field. So it will be like independent text or independent sequence of activations.
Hi, Ibrahim, I have a question.
Yes.
Like, for example, using larger number of strides, for example, 2 and onwards, we reduce the size of the image, output image.
Yes.
So while using pooling, does that also reduce the size of the image, or does it only reduce the number of calculations?
No, it reduces the size of the feature map also. Right? It reduces. No, it's. I mean, we use max pooling to consolidate those feature maps like down sampling. We do down sampling, so we reduce also the size of. We reduce the size of the feature map. Right?
Thank you.
Do we have an example for max pooling here? So we can go back. you see, this is max pooling. The input image, its input image is 3 times 3, and we use the 2 times 2 max pooling of size 2, right? So what will happen? We will apply this one here. We will select maximum. We will put the maximum here. Stride equal 1, so we will move with 1 step. Maximum will be 5. We will go down here. Maximum is 7. We'll move 1 step. Maximum will be 8. Correct? So this one was 3 times 3. The output is 2 times 2. So we don't.
My question is that. Sorry to interrupt, but my question is still there. Like, for example, if we do not do max pooling here, we do element-wise multiplication, the output would still be 4 by like 2 by 2.
Yes.
The max pooling is just an alternative to the element-wise multiplication. Am I right?
Yes. Right. Yes. It's not element-wise multiplications. We just select max. We don't do any max element-wise multiplication here. We select max. Right? It's max. This one, it's max pooling, right?
Okay.
So
it's just
we cover that part and we select max. We cover that part, we select max. We cover this one, we select max. Here, max.
Okay.
Right?
Thank you.
So the input image, it was 3 times 3. The output image is 2 times 2, which means the size has decreased, right? And then when the size has decreased, as I told you, when we decrease the size, it will impact the fully connected layer at the ends, because the all those sizes of future maps will be reduced. So when we flatten it, it will be much shorter vector. Because if we didn't use max pooling, this one will be 3 times 3. If we don't use max pooling at all, so you will keep the same. The feature map will be the same as the input image. Maybe if the input image was 200 times 200, so it will stay 200 times 200, correct? So it will be a huge number. It will be millions and millions of weights. And then when the number of weights increases, the model capacity will be high, and the chances to overfit will be much, much higher.
For example, if we're not doing the max pooling, how would we get the same output? Like if we do element-wise multiplication, do we get the same number of output?
If you will not use max pooling?
If I do element-wise multiplication instead of max pooling.
Yes.
So I still get 2 by 2.
No, you will not get 2 by 2 because it will be like a kernel, right? It will be element multiplication. It will be like a kernel. So you will apply this kernel here. So, but we need to know, maybe this is 1, 1, 1, 1, correct? So it's 2 times 2, and each element is 1. Element by element multiplication, because in max pooling we don't have any parameters, we don't have any filter. But I understand you. So imagine that we have this. It will be like convolution. So we will have like kernel. This is 1, 1, 1, 1, right? Each element is 1, and then we will do element-wise multiplication. So this is my image.
You have to adjust the camera.
Okay.
Can you rotate the camera, please?
Yes. So I mean this is it's a kernel, right? So and this one it's 3 times 3, so it will be like this one. So first we will apply it here. So what are those numbers? It's a 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, right? So now we will apply this one here in that part. So it will be 0 plus 1 plus 3 plus 4, correct? So it will be 8. So the output here.
Ibrahim, can you rotate the camera, please? It's still focusing on the slides.
Okay.
It's quite zoomed.
It doesn't listen to us. Okay, it's coming. Can you see my screen now?
Yes, I can see.
Okay, so I have this kernel, for example. We will apply it to that part, right? We will use element-wise multiplications. So it will be 0 times 1, 1 times 1, plus 3 times 1, plus 4 times 1. So it will be 8. We'll have 8 here. Stride equal 1. So S equal 1. So we will move 1 step. So we will apply it in that part. So it will be 1 times 1. It will be 1 plus 2 plus 4. So it's 7 plus 5, it's a 12, so this one will be 12. We will go down one step, so we'll apply it here. So it will be 3 plus 4, which is 7, plus 6, 13, plus 7, it's 20. This one will be 20, correct? We will move one step, so it will be 4 plus 5, it's 9. 9 plus 7, it's 16. 16 plus 8, it's 24. So it will be like this one. So the size will be the same, correct? Because we didn't use zero padding here. We didn't use zero padding. So the size will shrink if you didn't use zero padding. So the size anyway will shrink if you didn't use zero padding. We will use this valid, right? So if we select valid, so the size will shrink by this size minus 1. Remember, this one is 2 times 2. So it will be 3 minus 2 plus 1. 3 minus 2 plus 1 is what? 2. So it will be 2 times 2. So the output, this one, it will be 2 times 2. So if you want to use this element-wise multiplications, I don't know why this one is. Okay. Yeah, but it's I guess it's AI. So. So anyway, we will shrink. We will, as in the size will be much less if we didn't use zero padding, right? Because here we don't use zero padding. If you want to keep the same size, we need to use zero padding. But in this way, it will be like convolutional layer. It will not be max pooling. So we use max pooling to downsize the feature, the size of the feature map.
Okay, thank you. Now I got it.
Okay, so. So convolution over volume. So I mean, it's when it's a 3, when we have, for example, RGB image. So suppose instead of working of having a 2D image, for example, we have 3D image, input image of shape 6 times 6 times 3, and this is the case of all RGB images. So how the kernel will look like? So so each image is represented by height, width, and number of channels. So how we will apply convolution on this image? So we will just use 3 times 3 times 3 filter instead of 3 times 3, right? Keep in mind that the number of channels in the input and the filter should be the same. After convolution, the output shape is 4 times 4 matrix. So in fact, you will have 3. Each one will be applied to one channel, and you take the average of the 3. So the average will be here. So this one will be 4 times 4, right? The feature map. So it's like, so this one, it's RGB image. We will apply 3D kernel, right? This kernel, it will be 3 times 3 times 3. It's like neural network. It's like a neural network with 27 inputs.
We have to allocate each filter to each layer in the first layer, or it is random?
No, it will be automatically done.
Okay.
I don't know in which order, but it's like a neural network. It will be like, you know, when it's 3 times 3, it's like we have neural network with 9 inputs, correct?
Yeah.
So it's omega 1, omega 2 until omega 9. When it's 3 times 3, it will be omega 27. So it will be the same, but we will have more weights, omega 1, omega 2 until we have omega 27. So we will apply it to, I mean, we will apply it to this one, right? To the green one, to the blue one, and then we will get the output here in that place. So the feature map, it will be 2D feature map. It will not be 3D feature map.
Yeah.
Mm-hmm. So after convolution, the output shape is 4 times 4 matrix. So the first element of the output is the sum of the element-wise product of the first 27 values from the input, 9 values from each channel. We will get 9 values from each channel and 27 values from the filter. So after that, we convolve over the entire image. So in fact, only the input volume will be 3D, but the feature maps will be 2D. Multiple filters, for example, instead of using just a single filter, we can use multiple filters as well. How can we do this? So let's say that the first filter will detect the vertical edges, and the second filter will detect horizontal edges, right? I mean, when you have an image, maybe we need to apply 2 filters, one to detect vertical edges, one to detect horizontal. So we will apply multiple filters to each image. right? You need to decide this. You need to select, do we need 32 feature maps, right? Each feature map will be something. Maybe one of them will be vertical images, vertical edges, one will be horizontal edges, one will be gradient somehow, vertical gradient, horizontal gradient, right? So, so if we use multiple filters, the output dimension will change. So instead of having 4 times 4 output, as in the above example, it will be 4 times 4 times 2, correct? So when you select we choose the filter size, it's 3 times 3, right? But you need to decide number of feature maps. If you said, okay, I need to get 2 feature maps. So in this case, I need to get 2 from this one and another one, right? Each one will generate a feature map. So one layer of a convolutional network. No, I don't need to describe this, read this, because we describe this again. I mean each one, it's just so it's like in feed forward, one feeds forward a perceptron, for example, or something. So Z, in fact, it will be omega A plus B. A, it will be the pixel values of the input volume. Omega, it will be weights, and we will apply it to activation function. So we do, it's like this one, in fact. So we are just doing this 4 times. So we have this one, right? And we will we just element-wise multiplications, take summations, apply this summation to the activation function. So in our case, we just go ahead. So pooling, it's just repetition. We did this pooling layers, but it's just in more details. For example, we just apply those pooling layers, and we can just get the maximum. So it will be 9, it will be 2, it will be 6, it will be 3, right? So the dimension of the feature maps after pooling, it will be reduced. So we use it for down sampling. You can use max, you can use average, and as I told you last time, you can just invent a new approach and test it. So in example, this is AlexNet, and this AlexNet is 16 million parameters. So AlexNet, we have AlexNet. So this is the input volume. It handles RGB images of size 227 times 227 times 3. So this is input volume, and it consists of number of convolutional layers. So the first convolutional layer, this is the kernel size, 52 times 52, and we need to extract 96. We need to extract 96 feature maps. So sorry. The kernel size, it's 11 times 11, 11 times 11, and stride equal 4, right? And the feature maps, it will be 55 times 55 times 96, right? So this is the feature maps. So we need to get 96 feature maps. The kernel size is 11 times 11. We use stride equal 4, right? And after that, we will apply max pooling. The size of the max pooling is 3, so it will be 3 times 3, and then we will move with a stride equal 2, right? So in this case, the output feature maps, it will be reduced into 27 times 27 times, of course, 96. 96 will not change. This is the number of feature maps, right? So we don't sample. So now we are going from 227 times 227 to 27 times 27. And we will get 96 feature maps. Each feature map will be something different. Maybe one of those will be vertical edges, one of them will be horizontal edges, and so on, right? After that, we used here padding. So the size will be the same size, 27 times 27. The kernel size here will be 5 times 5. So we get, but we selected 256 features. So we are getting 27 times 27 times 256. We will apply max pooling, 3 times 3, with a stride equal 2. So it will reduce it to half. So it will be 13 times 13 times 256. So number of parameters decreases. After that, we will apply padding and a filter Now we are just, this is the feature map, right? We will apply convolutional, the convolution layer. So it's convolution, it will be 3 times 3, same padding, 0 padding, correct? So it will be 13s times 13s times 384, right? 384, so we selected 384. We will apply again convolution, right? 3 times 3, maybe the same 0 padding also because we still have the same size. So it will be 13 times 13, 384. Repeating it one more time, but in this time we select 256. So do you know, when we are here, we try to select the numbers which is easy to multiply, 256. So it will be 13 times 3. We will use max pooling. It will reduce this one to half. It will be 6. So it will be 6 times 6 times 256. Flatten. So what will be the size? Just multiply 6 times 6 times 256. We will have those number of elements. We will flatten all. We will put it in one vector of size 9,216. So this is flatten. In fact, this one does not have anything, does not have any parameters. We just flatten it, correct? We change the dimension from 2D to 3D into 1D. This one, it's a 3D vector or tensor vector, for example. We will convert it into this 1D. After that, we will use fully connected layer of this size. I mean, look, this size is 9,000, so I cannot go from 9,000 to 1,000. We need to go gradually, right? So from 9,000, we will go to 4,000, another fully connected layer of 4,000, the same size. And after that, we will use softmax with 1,000 outputs. 1,000 outputs, in fact, because this AlexNet has been trained to detect 1,000 objects, right? So now we are just, if you want to calculate those 60 millions, just multiply all those numbers and summing, multiply and sum to get the total. So it's 60 million. It's a huge 60 million weights. If we need to use this one, it works with, it deals with RGB images, correct? RGB images. And this one, it's for feature extraction. So you will have image of this size. You will extract those feature maps, right? If you want to import this one and use it for another problem, for example, driving license, those license plates and stuff like this. So I need to get that part. And here I will make this one different according to my problem.
Ibrahim, can you rotate the camera to the slides, please? We cannot see your hand.
The slide?
Turn the camera.
Okay.
Turn the camera.
This is problem. We need something smart. So it can track people and just, yes. There is in fact intelligent camera which track people and so it can just track you.
Yes. Track everything.
Yes. So here we have this AlexNet, and the AlexNet, it has been trained using a number of maybe 30 millions, I guess, images, and it has been trained by Google. So the input volume is an image of this size, 227 times 227 times 3. It's a 3-channel image. So we have RGB image. So here we will select. They selected. The filter size is 11 times 3 times 11, stride equal 4. So from this one, we will get this feature maps. They selected 96 feature maps. So we will get 55 times 55 times 96 feature maps. So this one, we will apply max pooling. The max pooling will be 3 times 3, stride equal 2. So this one will be reduced to half. It will be 27 times 27 times 96. Apply convolution. Using same padding and the kernel size 5 times 5. So and selecting and or choosing 256 feature maps. So we will get 27 times 27 times 256 feature maps. Apply max pooling again. This one will be reduced into half. So that without sample. So it will be 13 times 13 instead of 27 times 27. We will apply after that. List or 3 convolutional layers. We will apply 3 convolutional layers using same padding, right? Same padding and the filter size or kernel size 3 times 3. So at the end we will get 13 times 13 times 256. We will apply again max pooling. So when we apply here max pooling, it will reduce this one into half the size, the original size. So it will be 6 times 6 times 256. Multiply those and flatten them. When we flatten it, we will have 1D vector of size 9216. And after that, we will have two fully connected layers. In fact, two hidden layers and one output layer. So we will have two hidden layers, two fully connected layers of size 4096. And after that, the output layer will be softmax, which has 10 values. So if we need to calculate numbers, so it will be 1000 times this one, plus this one times this one, plus this one times this one, correct? Plus this, and so on. So we should reach 60 million trainable parameters. If you want to use this one for transfer learning, for example, you are working now on a project, you can just use AlexNet, apply it to first we need to resize the input image to be the same size here, because this one has been designed for 227 times 227. So we need to apply it to the same image size. So if your image is 32 times 32, so in this case we need to use interpolation and upsample. Is it called upsample? So we need to resize it. We need to just resize the image to be in the same size here. And after that, we need to select, we need to change this one according to our problem, for example, right? And then when we train this model, we will freeze those weights, those 60 million weights. We don't need to touch them because it's huge. So we need to freeze all those convolutional layers, and we will train only the weights of the fully connected layers. Right?
Yeah.
And I guess last time Muhammad Saad, he has been using VGG16. In PureNAR, you have been using YOLO. So many people have been using those transfer learning or pre-trained models.
Yeah.
Because all images have the same features. And if we have a model which can extract good features, it should be possible to apply the same feature extraction module or block into any kind of images. Yes, Hamid?
I have a question. Like after the first step, 50 we get output of 55 times 55.
Mm-hmm.
That's the side of the feature map. And then 96. It means that we are applying 96 filter or kernels onto the input.
Yes, correct. We're applying 96 kernel. Each kernel will result in a different feature map. Yes. After that,
when the 96 kernels, 96 feature maps becomes 256. Like now in this case, each of the input or the output of the previous one is being multiplied or being applied by 256 different features or different filters.
Yes, correct. Here, and I mean here we did max pooling. So this max pooling will reduce the size into 27 times 27. So now we are here with this feature map. Here we will apply 5 times 5, and we need to get 256 from this one. Right?
So like each of the input is being applied with 256 filters, or
no, 96
are being applied.
96.
Okay.
So the dimension, in fact, we selected this one 5 times 5, right? But in fact, those 5 times 5, it will be applied to 96 features in parallel. Can you see, like RGB image here? Do you see here? This one 11 times 11, but we didn't multiply it by 3, correct?
Yes.
Do we? We didn't multiply it, but in fact, this one it's 11 times 11 times 3, because here we have 3 channels. So it's the same here. It will be 5 times 5 times 96, correct?
Yes, I got it now.
Mm-hmm.
Sorry, Ibrahim, I was going to ask the same question.
Mm-hmm.
So normally when we moved from 3 to 96, we don't include 3 because 3 is the same like including 1 since it's 2-dimensional, even if it's RGB. So we multiplied by 96. And then 96 we have in the max pooling, which makes sense because we are keeping the same number of kernels.
Yes.
However, from 96 to 256, I did not get it. Normally, if we divide 256 by 96, it gives us 2.66. It's like we have applied 3 more kernels, because normally we multiply the number of kernels by the 96 to give us the new number, 256. Am I right?
Yes. So I will plot it here, Ahmed. Can you see my screen here?
No. Yes, now we can. Yeah.
Yes. Okay. So I will do it for 3 times 3 to make it easy, right?
Okay, thanks.
So imagine we have this RGB image. So the input is RGB, right? No, I will start with just not RGB, just grayscale. So when it's a grayscale image, it's only one channel. So imagine that this one, it's a 32 times 32 times 1, which is like endless data sets. So it's this one is 1, and we will use 3 times 3. And how many features you want to get from this one? So 16, 4 features, right? Is it okay? So in this case, in this case, we will have 4 kernels, right? We will have 4 kernels. Each kernel will generate 1 feature map, right? So this one, in fact, it will generate the first pixel here. This one will generate the first pixel here when we apply it for the first time. So we will get 4 feature maps when we move. So this one, we will get 4 feature maps. So 4, from this 4, we will get 4 feature maps. How many parameters here? We will have 9. So each one will have 9 parameters, right? So it will be 1, 2, maybe this one, it's 9, 8, 7, 6, like this one, correct? So how many parameters here? How many parameters in this one? How many parameters? 3 times 3 times 4, right? So the number of parameters will be 3 times 3 times 4, okay? Plus 4, okay? Now let us imagine that this one, we have 4. This one is 4. So I will add this one, it's RGB, this one will be R. We will have another image here. I was supposed to select. So RGB. Now this one, it's multiplied by 3, correct? So how can we deal with this one? I mean, in Python, in fact, in Keras, you just select 3 times 3 and it will automatically adjust it, right?
Yes.
So in this case, this one will be 3 times 3 times 3, correct? This one will be times 3, right? So number of parameters here will be 3 times 3 times 3 times 4 plus 4, correct? I will draw it here just for one of those. So one of those, instead of having 9 weights, it will be 27. So we'll have 1, 2, maybe this one 27, 26. So it will be like this one, right? If this one, it's if I'm working with feature maps, which is 96, so it will be 3 times 3 times 96. Is it okay, Ahmed?
Yeah. Okay. And the second, now it's clear. The second one, when we applied 5 multiplied by 5, is the same padding. We haven't changed anything.
We go back again here. Maybe we need to change the battery here. Okay. So when we apply here 5 times 5, yes, it will be because we apply here convolutional layer. This is max pooling. So the output from the max pooling will be 27 times 27 times 96. Now we will apply filter size 5 times 5, and we use same padding.
Okay.
So the size of the output will be the same as the size of the input. The size is height and width, height times width, correct? So the height will be 27, width will be 27. So it will be 27 times 27. But how many ones you want to get? How many feature map you want to get? I want to get 256.
Okay.
So the number of parameters here, in fact, it will be 5 times 96. We need to do an example. In fact, we need to define it with some, because the input dimension, we need to define the input dimension in Keras. In the input layer, we need to define the input dimension, right? So when you define the input dimension, I will mention that this one will be 3. So 3 will be considered into those this configuration, for example. But for the feature maps, it will be automatically transferred from one layer to another layer. So we will apply here the same. We will get the same size, 27 times 27, and the number of feature maps. We need to decide how many feature maps we need to get. Yes, Ahmed?
Okay. So, for example, if we are going to select 96 features, so are we going to give a manual input of the feature or the filter?
No, no. It's you just this is the feature. This is the filter size, which is
You're just
2D.
going to give the filter size.
It's only 2D, by the way. We don't define it as 3 times 3 times 3. We don't define it. We just define it as just height and width, and the number of channels. It will be automatically transferred from one layer to another layer. You just need to define it for the input image, in fact, or only the input. So in Keras, we don't.
I'm talking about the number of features.
Yeah, you define it.
But there are.
Yeah, you define it. You need to define it.
Right. So we need to make sure that we are, for example, if the size is, for example, like 3 by 3 of the field of the output, and if we are going to give like insane amount of features, like for example 60, so a 3 by 3
In fact,
matrix 60 different features doesn't make sense, right?
yeah, I know people are confused. This one, it's not the parameters. This one, it's the size. This is the size of the feature map. It will be a matrix of this size, right? This one, it's a size, and it's not the number of parameters. So, is it? But do you feel that people are confused between size and size? Number of parameters and size? So this one, it's the size. So the input volume has this size, 227 times 227 times 3. This is the size of the feature maps. It will be 3D matrix, 55 times 55 times 96. This is the size and not the number of parameters.
So 256 are not the number of parameters.
No.
Or features.
No. So the number of parameters here, it will be 11 times 11 times 3. Number of parameters here in this layer, in the first convolutional layer, it will be 11 times 11 times 3. Number here of parameters will be 3 times 3 times 69 plus 69, correct? No, sorry. So yes, plus 69. So again, one more time. Number of parameters here will be 11 times 11 times 3 times 96 plus 96. Is that correct?
Okay.
So Ravi, are you Ravi? Who is talking
No,
to
I
me?
am Saad.
Hello, Saad. So this is the first convolutional layer. So if the input volume is 227 times 2227 times 3, the output volume will be the size, 55 times 55 times 96. How many parameters here? Number of parameters here will be 11 times 11 times 3 times 96, because we will repeat this 96 times. Correct?
Okay, and then we add 96.
Yes, when I apply this one time, 11 times 11 times 3, I will get one feature map. When I apply it one more time, I will get another feature map. We need to apply this 96 times. Right, Saad? We need to apply it 96 times.
Yeah.
So how many parameters here? It will be 11 times 11 times 3 times 96 plus 96. Right?
Okay, now I got it. So
You got it?
So my question is now that, yeah, I got this now. So my question is now that, for example, we have to apply the parameters of size or the feature of size 11 times 11 times 3, 96 times.
Yes, correct.
So all these features would be different and we have to define them manually.
Yes, manually. It's
Or not?
hyperparameter. It's hyperparameter. You select it by yourself. Right?
Okay. Now I got it.
You train your
Now
model.
everything is clear.
You need to select the kernel size, right? Only in 2D, right? In 2D, just 2D. And you need also to select number of feature maps, which we need to get. So here, for example, here we have this one is convolutional layer because we just finished this max pooling and we are here. This is convolutional. Now we need how many parameters here in this layer? So by the way, it would be nice if we can calculate it. So we said 11 times 11. I will not x because x make people confused. 11 times 11 times 3 times 96 plus 96. Can anyone calculate this number? So the second layer, which is this one, it will be 5 times 5 times 96. It will be 5 times 5 times 96 times how many features? 256 plus 256 equal. We need to get this number. We will use max pooling, so we will get this one. So here we will apply this convolutional. It will be 3 times 3 times 256. 3 times 3, 256 times how many? 384. 384 plus 384. We need to get this number. Can you calculate, please?
The first one is 34,944.
Can you calculate total number?
The first line.
No, we just do it for all,
Of course.
right? So now we finished this one. We will not use mere max pooling. We will use another convolutional layer here. So it will be 3 times 3 times 384. 3 times 3. 3 times 3 times 384 times 384 plus 384. Now we are here. This one, it will be 3 times 3 times 384. 3 times 3 times 384 times 256 plus 256. Okay. Now we finished this one. We will get max pooling, and after max pooling, we have 9216. 9216. It will be, so this is fully connected one. Fully connected one. So I will call this one convolutional layer 1, CV2, CV3, CV4, CV5. Correct? Fully connected layer 1, it will be 4096 times 9216 plus 4096. We have fully connected 2. Fully connected 2, it will be 4096 times 4096 plus 4096. Fully connected 3, which is the output layer, it will be 1000 times 4096 plus 1000. Can you get the total number? Can you see those numbers? Can people online, maybe they are
You need to rotate the camera.
yeah, I will try to adjust it. No. It should be. Sorry, I've been working here. Can you see the whole screen?
Yes, now we can see.
Okay, so we have convolutional layer 1. We have convolutional layer 2. We have convolutional layer 3, 4, 5. Fully connected layer 1, fully connected layer 2, fully connected layer 3. How many parameters? We need to have a calculator. So this is the number of parameters in the model. This is the number of parameters. But what we are seeing here, in fact, those are the size of input volume, feature maps. Do you need,
Yes, I'm doing it.
okay. You can come here.
$62 million and
And
2,378,000.
okay, 62,700,000.
No, 378,000.
378,000.
344.
44. Okay, so it's more than 60 million. So this is correct. I don't know the exact number. In fact, you can make it in Python and you can get all numbers, right? Because we know the structure. So we can put it in Python now. So maybe Muhammad, you can just do it in Python, in Colab, and share it with us, for example, the structure of AlexNet. Because we know the structure, we know all parameters. So we can reconstruct it. But it has 62 million parameters. So, and imagine you are working with a data set of 10,000 values. Is it enough to train such kind of model? No. Such kind of model, maybe you need 30 million images or something, right? If you use your 10,000 data points, maybe the model will go for overfitting quickly, right? And this is, we used the max pooling, we used stride equal to. If we didn't use max pooling and stride equal to, for example, I mean, the number will explode, in fact. It will be much, much bigger. Yes.
Yes, if I can, Ibrahim, can I?
Yes.
Yes, because I remember I was reading a paper about this AlexNet, and I have shared with you guys a document that normally, if you want, I read the document as well as how they are calculating from 27, for example, to 27. So, for example, from 27 to 27 over there is they have used the kernel of, as you said, 5.5 and with a stride of 2. So if we put 27 minus 5 and then we add 1 and then we multiply it by the number of the stride, it's going to give you that number. So if you follow the document that I have sent you, you will get better understanding of how this multiple calculation has been made and how do we get from these numbers to the other numbers. They have like a full architecture and philosophy design of the AlexNet.
Yes, I mean, because now we are using max pooling.
Yeah.
And it's 3 times 3, and we use a stride equal to. So we have those formulas in the previous slides. So you can get the size of this one. Right? It will be n minus 2f plus 1 divided by, you have those equations which we just mentioned. So you can use those equations to get this size. Because we have the stride, we have f. This one, it's f, in fact, stride. Now, this is max pooling, P. This is S, this is the filter size. The input image, it's 55 now because we're applying it to this one. So using those equations, you can get the size of the output volume, for example.
Yeah.
And how we calculate a number of parameters, we just did it. So in first convolutional layer, here, it will be 11 times 11. Here, it will be 11 times 11 times 3. And if we did that one time, we will get one feature map. So we will multiply it by 96 because we need to get 96 feature maps plus 96. So this is the number of parameters here. After max pooling, we have here convolution. If we need to get number of parameters here, it will be 5 times 96. If we will do it only one time, but we need to do it 256 times. So it will be 5 times 96 times 256 plus 256. And just we can just continue and summing all those numbers, so we will get a total number of parameters. Yes. So any question for this one? So do you want to take a break or should we continue? Should we continue or do you want to take a break?
Break.
Okay, we can take.